Let's get started with model checking, in which we are going to enumerate all possible models using truth tables. Okay? So a model is simply an assignment true or false to every propositional symbol in the sentence or the formula. And what we need to do is to check that actually the formula or the sentence alpha is true in every model in which the knowledge base is true. Okay, so I'm going to check by examining this truth table whether we could find that alpha is actually true whenever KB is true. Let's now consider the set of rules we built in the knowledge base to represent the reduced 1 plus word, in which we used a set of 7 propositional symbols, B11 through P31, and wrote a set of 5 rules to represent the knowledge base. So in this case, the knowledge base could be written as actually the rule 1 and the rule 2 and the rule 5. Okay, so all these elements has to actually build or make the knowledge base. All right, so we have 7 propositional symbols, and we're going to talk about truth table on this knowledge base. So we're going to check the models or the assignments of true or false for each of these propositional symbols. So in total, we have 2 to the 7 equal 128 possible rows in the truth table. We're going to just focus on these 3 lines here in which the knowledge base is true. Why? Remember, we wanted to answer the questions such as, does KB entails the proposition P11? Does KB entails the proposition P22? Okay, so far these are questions, and we don't know. We want to use model check-in, right? Model check-in to actually check the truth value of P11 whenever K, the KB, is actually true. All right, so KB is true in 3 out of 128 possible rows. So I'm going to focus on this 3 lines here, or 3 rows here. I'm going to check that actually whenever the knowledge base is true, we have P11 is actually false, in which case we could infer with confidence that KB entails the negation of P11. Okay, so this is not a question anymore. All right, so we know that by model checking that P11 is KB entails the negation of P11. All right, so it's not the case for P22. So if you look at P22, we have P22 could be either true or false based whenever KB is true. So we can't really say that KB entails P22, at least at this stage in which the agent explored the bottom left corner of the environment. In a similar way, we could check whether actually P12 is true or P21 is true. And just like P11, we have KB entailing the negation of P12 and KB entailing the negation of P21. All right, so this model check can help us actually derive knowledge about the truthfulness or the validity of these kinds of formulas, and can help then the agent move in its environment. Now, suppose we don't have model check-in as a tool. We only can do inference using modus ponens and whatever equivalence propositional logic formula we found earlier. All right, so no semantics at all, just syntax. So we're going to focus on the knowledge base of the reduced 1 plus word, in which we have the rules R1, R2 through R5. So what we want to prove here, for example, is that let's say KB entails the proposition P12. That's a question. And whether KB entails the proposition P21, and that's another question. Okay, so can we use inference rules on this knowledge base to actually derive information about whether this is true or false and whether this is true or false? All right, so first observation, P12 and P21 appear in this in the rule number 2, this proposition here. So we can just focus on this one for now. This one does not have P12, P and P21, so it is unlikely that this rule will lead to, through inference, to this 2 element that we are trying to prove. All right, so we are starting with the rule R2, right? So the rule R2 says that breeze in 1-1, if and only if we have a Pete in 1-2 or a Pete in 2-1. Okay, so this is the first rule. This is a rule that we know is true. There is a breeze only if there is a Pete in the adjacent rooms. All right, so from this one, we're going to make an inference. Usually we like to draw a line, so this is a line. And this line will be an inference based on the bidirectional or the if and only if splitting into 2 implications. So I'm going to write this as actually as a B11 implies P12 or P21. And I'm I'm going to put that in another color, and we have P12 or P21 implies B11. It's good to use, it's a good habit to use parentheses to show that we have these two elements here, proposition P and proposition Q. All right, and we want to see what we could do that with that next. So let's call this proposition rule R6. R6. All right, so from R6 what we can do, so remember if we have proposition P and proposition Q, then we could infer P. And we could also infer from P and Q, we could also infer Q. And the reason is that if this is true, it's guaranteed that both of them are true based on the definition of the connective of conjunction. All right, so I'm going to focus on either or of these parts. I would rather say, let's pick one of them. I would pick this one first, and I will tell you why later. So we have P12 or P21 implies B11. This is by the definition of actually what's of the conjunction in inference rules. If you have the conjunction, you could infer any side of the conjunction. Okay, great. So why I'm using this one, because I see that I have B11, and I want to have actually to be able to infer through modulus ponens either P12 and P21. And remember, for modulus ponens, if we have P and P implies Q, I can infer Q. But you would tell me that this is actually not on the right side, and I would tell you that actually I don't have B11 either. I have not B11. So I'm going to use the trick of the contrapositive to flip this implication. And in this case, this is the contrapositive. Using the contrapositive, it's possible to rewrite this formula as B11 implies the negation of P12 or P21. Okay, so I'm trying to put this on the side, but I'm taking also care of having the negation of B11 on the left-hand side. We could also use actually the modulus tollens instead of modulus ponens if you want to keep it as is. But let's do it this way first. All right. So from this, what I can do is I see that I have something that looks very much like modulus ponens. I have P, I have Q, and I also have P here. So I'm going to write this rule R4. But maybe before I do that, let me try to break this down, because it's the negation of the disjunction of P12 and P21. So I'm going to do use De Morgan's law, in which I'm gonna distribute the negation. It's gonna be which will give me the negation of B11 implies not P12 and not P21. Right? So if you check the properties, we have De Morgan's law that actually have this property of distributing the negation and changing the disjunction into a conjunction. Okay, great. So I start to see things coming up. I have P implies Q, and I have P in R4. So I'm going to write R4 here. So I'm going to write R4 here. R4 is what? I have the negation of B11. Okay? So check this out. We have the negation of B11. We have P. P implies Q. So I could use modulus ponens, this rule here, to infer that actually by modulus ponens that I have negation of P12 and the negation of P21. All right. So from this, I'm getting close to showing these elements here. So from this one, this is the conjunction of these two. So if this is true, again, by using the conjunction, and I meant to use the red here, so that I'm doing the inference here. So I'm going to infer that I have P12, and I can also infer that I have P21. Okay? So what I proved just now is that actually the knowledge-based infers or entails the negation of P12, and it entails the negation of P21. All right? So you could think of doing a similar thing. I will leave that as exercise. Right? So try to prove P22 and P12 using the third rule, R3. All right. So here it's important to observe that I didn't use R3 at all. I just used, we ignored it altogether. I just used R2. I used R4, right, to prove that actually I can entail negation of P12 and negation of P21 without even enumerating any model or building any truth table. You might have noticed something from the previous example, which is that inference sounds like search. I'm searching to what rules to apply, what inference to do to achieve some goal, which is to prove entailments between the knowledge-based and the proposition, right? So it's possible actually to cast the problem of inference as a search problem and use any of the algorithms we have seen in the previous weeks. So the way to formalize that is to use an initial state in which we use the knowledge base. This is the set of rules R1 through R5 that I had before. The action would be all the inference rules applied to all sentences that match the top of the inference rule. So the top of the inference rule also, as I said, called premise. So we have each inference rule would be a premise and a conclusion, right? So I'm going to apply the set of actions would be all the inference rules that are applied to all sentences that match the premise of the inference rule. So we're going to explore the possible actions on all the inference rules. The result will be to add the sentence that are in the bottom half. So whatever conclusion you get, you're going to add that to as a result of the knowledge base. Now the goal would be a state containing the sentence we are trying to prove. So for example, in the previous example, I wanted to find whether KB entails P112 or P22 or P1, the 4 possibilities. So suppose we have KB, I wanted to know whether KB is P12, so I just need to focus on this one as the goal, right? Start this as the initial state and try to imply all possible rules until I reach the result P12 or the negation of P12. So it's possible to just use any search problem algorithm to reach the goal of doing inference just based on the syntax, and again without using any model checking.